Welcome to EDU World Space.
So for our space vehicle, let's write down the motion of the mass center. Remember, there's no external force, so there's no effect due to gravity. So the motion can be written as r bar is equal to v naught times t. So v naught we are given is 360 meters per second along unit vector I, and multiplied by time 4 seconds. And so we get a position vector of 1,440 meters in the I direction after time 4 seconds. We also know that the center of mass is defined as follows. So the mass of the system, after it has split into 3 fragments, m times the center of mass, r bar, is equal to the sum over the mass of the individual fragments multiplied by their position vectors. So mi times ri, a scalar product. Now m times r bar is the mass of the space vehicle, the mass of the entire system before it fragments, 300 kgs, multiplied by the center, 1440, in the I direction. And this is equal to the mass of fragment A times the position vector for fragment A plus the mass of fragment B times the position vector for fragment B plus the mass of fragment C times its position vector. So this is MA times its position vector, 1170I minus 290J minus 585K plus the mass of the second fragment is 100 kg multiplied by its position vector, 1975I plus 365 J plus 800 K. And finally, for fragment C, we have the mass of the fragment is what's remaining, is 50 kg, multiplied by its position vector RC, which we wish to calculate for. So we can simply rearrange this equation, solve for the like components, the I, J, and K components respectively, and hence we are left with the position vector for fragment C after time 4 seconds, and we get RC to be 1180 meters in the I direction plus 140 meters times unit vector J plus 155 meters along direction K. And that's our position vector for fragment C after a time of 4 seconds has elapsed.